So now let's dive into solve a system of first-order linear ordinary differential equation. Well, I need to find the eigenvalue and eigenvector of the coefficient matrix. And when I try to find an eigenvalue and eigenvector of the matrix A, B, C, D, I want to find the corresponding characteristic equation for it, which is r squared minus a plus dr plus ad minus bc, which clearly is a quadratic equation. Therefore, I'm expecting three cases of the solution. So I'm expecting two distinct real solutions, which eigenvalues, a pair of complex conjugate eigenvalues, and repeated eigenvalue. Well, I'm going to start from the simplest case. And just like the characteristic polynomial which we use to solve second-order linear ordinary differential equation, the distinct real eigenvalue would be the simplest case. We need slight manipulation for complex conjugate case and repeated root case. So for today's class, we are only going to discuss that. We're going to discuss the other part when we come back and teach the material face-to-face. So if we have distinct, so two different real eigenvalues, you would find the two eigenvalue R1 and R2 separately, and you will find corresponding eigenvector K1 and K2. In this case, K1 is a vector which has two entries, right? So for simplicity purpose, you can write it as I don't know what's the best way to write it. Let's deal with that a little bit later. But bottom line, you are expecting a vector which has two entries. You are expecting another vector which has two entries, right? So you should have typed it out in bold instead of this case. And then once you find them, then the solution of the differential equation is K times ERT and K times ERT. They are supposed to be linearly independent based on discussion from linear algebra, which we will not dive into details. Therefore, a linear combination of those two forms your solution. So let's try to put it into practice. I have a system, a first-order linear ordinary differential equation, which I've already put into the matrix format. How to change it from the standard structure into the matrix format, you should know that. So the differential equation is naively speaking equivalent to this, right? And we practiced transforming it earlier. So once we get this, I want you to find it. In our practice calculation, we did find a set of eigenvalue and eigenvector already, which is in our class recording earlier. So if I have already find this particular the structure of the eigenvalue, eigenvector already, it's just a matter of how to put them together. So my solution is going to be x1, x2 is supposed to be C1, which is undetermined coefficient, multiply the eigenvector, multiply e to the corresponding eigenvalue times t. Okay, they are going to be paired up. Eigenvalue and corresponding eigenvector. So again, eigenvector and e to the 6t. So this is what the solution is supposed to look like. If you want to make it look slightly more efficient or friendly, scalar multiplication is going to be multiply, right? It's no longer matrix multiplication, so it can multiply in. So you can see this is C1 negative C1 multiply e to the negative t. It is 3C2 4C2 multiply e to the 6t. So it's C1 e to the negative t, and then negative C1 e to the negative t, add to 3C2 e to the 6t, add to 4C2 e to the 6t. And because there's two rows, so I can write them out separately. It means the first function has a solution, C1 e to the negative t plus 3C2 e to the 6t. x2 has negative C1 e to the negative t, add to 4C2 e to the 6t. So for the system I try to solve, I'm going to get the solution as that, but I didn't solve it directly. What I did is I changed my system into a matrix format, and then I know what's the coefficient matrix. I find the corresponding eigenvalue and eigenvectors of the coefficient matrix, and I use the property of eigenvalue, eigenfunctions to write out the vector format of my solution. If you stop here, it's totally fine to say this is the solution of my expression, unless in the problem I said please write out their solution explicitly, do not use matrix or vector format, then you may want to write it out like that. Otherwise, that's perfectly fine, the structure of your final solution. And if you don't trust me, this is the solution, what we can do is we can do a very quick verification, right? Let's see. If I plug in x1, x2, the solution back into my differential equation, see if that works. So do my verification. Let's take a quick look. X1 takes derivative is c1 e to the negative t takes derivative, which is negative c1 e to the negative t. Takes derivative of 3c2 e to the 6t gives me 3 times 6, so it's 18 c2 e to the 6t. That's x1 prime. And let's see if 2x1, 3x2 add up together like the same thing. So 2x1 plus 3x2 is twice of c1 e to the negative t, add to 6 c2 e to the next 6t, add to 3, so it's negative 3 c1 e to the negative t, add to 3 times 4 is 12 c2 e to the 6t. Together, I end up with negative c1 e to the negative t and 18 c2 e to the 6t. So when I plug the solution back into my differential equation, I realize x1 prime, which is the left-hand side of my first equation, does equal to the right-hand side, which is the right side of my first differential equation. I can verify the x2 part very quickly. X2 prime from that is negative c1 times e to the negative t times negative 1, so it's c1 e to the negative t plus 24 c2 e to the 6t. And the right side of my differential equation says 4x1 plus 3x2. 4x1 is 4c1 e to the negative t plus 12c2 e to the 6t. 3c2 is negative 3c1 e to the negative t plus 12 c2 e to the 6t, which gives you c1 e to the negative t plus 24 c2 e to the 6t. As you can see, x2 prime and 4x1, 3x2, they are mathematically equivalent. So what I found does solve the original set of the differential equation. So again, the procedure, if you have your system, write it into the matrix structure based on the coefficient matrix, find the corresponding eigenvalue and eigenvectors. The structure is a linear combination of e to the eigenvalue times t multiply the corresponding eigenvector. If there were several, you're just going to put them together in the same structure. So this is how we work it out. And C1, C2 are undetermined coefficients. Unless there were initial function value given to you, I wouldn't be able to find them. So that's me jumping relatively quickly from knowing the eigenvalue, eigenvectors. So if we have a problem, how do we start from scratch, right? So now pretend I have the system given to you. What am I supposed to do is to find the eigenvalues first. So my matrix is 3, negative 2, 2, negative 2. You can jump to A minus Ri, find the determinant of it, or you can use the formulation of characteristic equation directly. So this is what I end up with. I'm looking for my R. Therefore, the determinant is 3 minus R, negative 2 minus R minus 2 times negative 2. You can either use this, carry out the calculation, or you use the characteristic equation memorized directly, which is going to be R squared. And then you are going to end up with minus 3 plus negative 2, which is going to be minus 1 times R. And then you're going to add to 3 times negative 2, which is negative 6, minus 2 times negative 2, which is positive 4. So you have R squared minus R minus 2 equals 0. So R minus 2, R plus 1 is 0. So R1 is 2, R2 is -1. So you find your two eigenvalues of this equation. You need to find the corresponding eigenvectors, which is what we have to do next. So find eigenvalues and then find corresponding eigenvectors. To find the corresponding eigenvectors, I'm going to start from here because that space below is not enough. To find corresponding eigenvector, you have A minus Ri times x1, x2 to be 0, 0. So start with 2. You have 3 minus 2, which is 1, negative 2, 2. You have negative 2 minus 2, which is negative 4. Multiply your x1, x2. And technically, I'm writing k1, k2 here. I guess that's a better idea because x1, x2 has already been used. So it's supposed to equal to 0, 0. So I have 1 times k1 minus 2 times k2 being 0. So if I have k1 being 1, my k2 is 1/2. So I end up with r being 1 and corresponding eigenvector be 1 and 1/2. Then the other one is a minus the r, the second r. So I have 3 minus -1. 2, sorry, negative 2, 2, negative 2 minus negative 1, right? It's minus the r of the diagonal entries. So this came from 3 minus 2. This came from negative 2 minus 2. So once you have your a minus r, it should be multiplied k1, k2. It should be the same as 0, 0. This corresponding to your r being -1. So what I end up with is 4, negative 2, 2, -1, and then k1, k2, and then I end up with 4k1 minus 2k2 being 0. So if k1 were 1, k2 would have been 2. So my corresponding eigenvector is k2. So how did we say about the structure? It is eigenvector times e to the eigenvalue times t. So I'm going to put things together following the structure. It is, my bad, it is 1, 1/2. It's e to the 2t. It is 1, 2. It's e to the -t. Those are the two basic structure of your solution. And let's put a linear combination between those. So that's what I should have as a solution of my final ordinary differential equation. But for this particular problem, I also said, oh, by the way, I know the initial condition. Your x1, x2 technically depend on t, so let's plug in the t. x10 is technically going to be C1. Let's keep reading the first row, right? The first row is C1 times the first row, C2 times the first row. Along the same line of thinking, x2t is C1 times 1/2 times e to the 2t, C2 times 2 times e to the -t, right? Second row, second row, second row. So when I plug in my 0, I should reach the first part and second part separately. So I'm going to end up with x10, according to the problem, is 1. Is supposed to be C1 times 1 times e to the 0, which is 1, by the way. Add to C2 times 1 times e to the -0, which is also 1. And the x20 is -1, if I remember correctly. That's right, -1 is C1 times 1/2 times 1, add to C2 times 2. So in short, my general solution leads to this particular structure C1 plus C2. -1 is 1/2 of C1 plus 2C2. So I can try to solve it. What I can do is I can multiply -2 to the second structure, so I can have a nice cancellation. So multiply -2 to both sides, give me 2, gives me -C1 minus 4C2. Now, the first row and the last row, when I add them together, I'm going to have a perfect cancellation. So I'm going to end up with 3 being C1 minus C1, C2 minus 4C2, namely negative 3C2. So C2 is negative 1, therefore C1 is 2. So what I'm going to end up with is my solution x1t, x2t is naively speaking C1 times 1 half e to the 2t add to C2 times 1, 2 e to the negative t. So this is the solution of my differential equation of the matrix format, and I want to write it into the non-matrix format. In general, you don't have to do it, but if that's required, you can write it out, right? Read the first row, read your second row, and you may simplify it along the way if you want to. So you could have said my solution is 2 e to the 2t minus e to the negative t. It's e to the 2t minus 2e to the negative t as my x2 of t. So this is how we take advantage of the property of linear algebra of matrices, use their eigenvalue, eigenvector, which are the intrinsic property of matrices, to find the solution of a system of a differential linear ordinary differential equation, which is also homogeneous. So that's what we have for now. Please make sure you finish watching the videos. The complex conjugate cases are much more complicated. The repeated eigenvalue cases are also complicated. So we're going to talk about that after we come back. I will put the worksheet online. I hope you get the chance to practice a little bit. Thank you. Have a good break. I will see you on Tuesday of the coming week.